Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, it's my pleasure to introduce Dhruv Batra. He's a research assistant professor at TTI Chicago. Last spring, he spent some time as a visiting researcher at MIT with Bill Freeman, where he's working on learning latent structural SVMs. Before that, he also interned at MSRC with Pushmeet. And before that, he was a PhD student at CMU underneath the he was being advised by Suhan Chen, and there he was working on co-segmentation using interactive methods of images. Thanks.
Thanks, Larry. Thank you all for coming. So I gave a talk here at MSR a couple of years ago, and I think one of the first things I said was, it's really nice to be here at Microsoft, and one of the things I've always wanted to do was give a talk at Microsoft with a Mac. That was 2 years ago. I've been doing that since. I've been giving a talk with a Mac. This trip, I forgot my dongle at home. And so yesterday I had to go to an Apple store and buy that. So I guess karma got its way for me making that remark. But OK, so let me begin. If I had to summarize, machine learning 20 years ago, or what we were doing in machine learning 20 years ago, this picture essentially summarizes what we were interested in, right? We were interested in partitioning two classes and finding best ways of partitioning two classes, right? Faces from non-faces, digit 3 from digit 6, chairs from tables, right? This is the canonical thing that we were interested in. And if I had to say what changed in the last 20 years, I would say, things that changed was now we're interested in much larger output spaces. We're interested in exponentially large output spaces. And I'll show what I mean by that. So segmentation, which is a problem that I'm interested in. You're given an image, maybe some user scribbles. Your output space is either at each pixel a binary label, 0 or 1, foreground, background, or some k set of labels that you know exist in the database. So the space of possible outputs is the number of labels to the power of number of pixels, right? That's the output space that we're essentially searching over. Or in object detection, where to find an object, we work with parts-based models. So we say a bicycle is made up of maybe a wheel, maybe a bicycle rim, or a person is made of these parts. We search for these parts. So where are these parts located? And then a spatial reasoning. So the output space in this case is the number of pixels, which is possible locations of these parts, raised to the number of parts, right? Again, an exponentially large output space that we have to search over. This can be not just in a single frame, but in video. So you're trying to do person layout in video. So certainly the exponent goes up by the number of frames that you're dealing with. Right? In super resolution, one of the fundamental models that we have is a graphical model which says, I'm trying to resolve this image into a much higher resolution. What I'll do is I'll collect a patch of low and high res images. Low and high res, I'll collect a dictionary of low and high res patches. And what I'll say is that for each input patch, I'll find the closest low res patch in my dictionary. I'll replace that by the high res patch, right? So the space of output, that you're searching over is basically your dictionary size raised to the number of input patches, right? So and again, an exponentially large output space. This is not just vision. People in NLP are really interested in these problems of dependency parsing. So there's a parse tree that tells you this word modifies this other word in the sentence, right? So it's a directed tree on the space of sentences, on the space of words. How many directed trees can I form? It's again n to the n minus 2, but that's the sentence list. So that's the space that you're searching over. And it could be information retrieval, right? So I go on my favorite search engine, Bing, and I search for some documents. The space of output space in this case is document factorial, right? That's the space of rankings that I have to search over, right? So in some sense, if we're on this side of machine learning, if we have to search over exponentially large output spaces, then we need to revisit some of the same issues that we addressed for the two-label case. We have to understand how do we hold distributions over exponentially large objects. So my running example would be segmentation because it sort of makes sense. How do I hold a distribution over the space of all possible segmentations which contain checkerboard segmentations, the stuff I'm interested in, all white, all black, all possible segmentations. Given this model, how do I perform inference in this model? How do I find the most likely segmentation I'm interested in? And learning, which is how do I learn this from real data, right? No expert is going to be able to hand this to me. All right, so my work has been on all three of these issues with structured output models. And today I want to talk about a couple of things, which is essentially I'll talk about this one work which we're calling the mbest mode problem. And I'll go into details of that. In the second part, so the first part will be a modeling and inference question. The second part will be a pure inference question. So, and time permitting, maybe there'll be some other teasers of things that I'm working on. So let's get started. So here's the problem that I want to talk about. This is what we're calling the mbest mode problem. And in order for me to tell you that problem, let me give you a model. And the model that we're going to be working with is a conditional random field, just so that I hand you the notation. We're given an image. There are some variables, so let's say pixels. I'm showing a grid graph structure, but I'm not making any assumptions on the graph structure. This is just a running example. Each pixel or node in my graph, I have some labels that I have to assign to. So this pixel might be a car, a road, a grass, or a person, right? So a k set of labels. Also, I'm handed an energy function which scores all possible outputs. Right? So somehow it gives me the cost of each output. And that is represented by a collection of node energies or local costs. So it might be a vector of 10, 10, 10, 0, 100. So because you're minimizing cost, this variable prefers to be the third label, which is grass. Right? Also at each edge, I'm holding some sort of distributed priors. So nodes that are adjacent to each other in this graph tend to take the same label. So this is just showing that if you take the same label, your cost is 0. If you take different labels, your cost is 100. Right? It's just encoding my prior information. And now the problem I'm interested, and instead of thinking this as a cost function, you could think of this as a distribution. If you just exponentiate the energy and you factorize it out by a constant, this becomes the distribution that I was showing. Right? That's fairly straightforward. It's a discrete space, so you can sum it out, and it's really easy to come up with a. So that summation computing that summation might be really hard, but it's really easy to think of this as a distribution. Now the task that we're interested in typically is, given this distribution, find me the best segmentation under this distribution, right? So, and that can be expressed as, given this cost function, find me the lowest cost assignment of these variables. I have some node potentials, edge potentials, find me the lowest cost assignment. That's my best segmentation, right? And this is too general a problem. In general, it's NP hard. I can reduce max cut to this. I can reduce vertex coloring to this. There are inapproximable problems that I can reduce to this. So this is not, in the general case, this is hopeless. And faced with an NP hard problem, you bring out your standard tool set. You either write down your heuristic algorithms, greedy algorithms, or some convex relaxations. But before we do that, before this turns into an optimization talk, let's think a second. Is computer vision really an optimization problem? Or is it just an optimization problem? Right? If you did have an oracle that could solve this optimization problem, would you be happy? Would computer vision be solved? And we've addressed that question before, and the answer is no. We've done large-scale studies. So in this paper by Talia Metzer and Chen Yanover, they found that if you do actually spend, if you take current instances on some data sets, take your models, run exponential time algorithms, and find the global optimum under your existing models, those global optimums still have some of the same problems that approximate solutions do. They tend to oversmooth, they miss certain objects, they're not good enough. In fact, even worse than that, which was worked on by Rick and others, if you actually find, if you compare the energy of the ground truth, turns out that the ground truth has much higher energy than the map, right? Turns out that your model thinks that the ground truth is much less probable than this other thing that it believes in. So not only are our models not perfect, when we spend more time coming up with approximate or better approximate inference algorithms, we've somehow moved away from the ground truth. More time you spend coming up in better algorithms takes you away from the ground truth in some sense. And that's sort of disappointing, right? The reason for this is somewhat obvious. Our models aren't perfect, they're inaccurate. They're not completely garbage though, they have some reasonable information in them. So while one solution to this problem might be just learn better models, right? Go ahead and learn better models. It seems simple enough. What I'm going to say is that you should be asking for more than just the map. You've learned this rich distribution from data or from an expert or from some source. Why extract just a point estimate? And the problem that I'm going to talk about, and some people have looked at this problem in the context of combinatorial optimization algorithms. This was called the M-best map problem. So instead of just the best solution, they will find the top K best or top M best solutions. Can anyone think of the problem with this approach? If you were to find the top M solutions, what was the problem that you'd run into? They'd be nearly identical. Any reasonable objective function is going to have some peak. When you ask for the top M solutions, you'll be nicely clustered around that peak, and these solutions are essentially useless for you. Right? What you'd like to solve is this M-best mode problem, where you can do some sort of mode hopping, where you want to know other things that your model believes in. Right? And this is the problem that we're calling the M-best mode problem. Now, I want to be a little careful. We're working with a discrete space, right? So this is not a continuous distribution. What does mode even mean? And I'll formalize that in a second. But before I tell you how we can find the M-best mode problem, how we can solve this, what would you do if you did have an algorithm that produced some diverse set of hypotheses? What would you do with it? Right? One thing that you can do is anytime you're working with interactive systems, anytime there's a user in the loop. So this is interactive segmentation, right? A person scribbles on an image, and you present to the person the best segmentation. Instead of just one best, you can present some 5 best, but you have to ensure that those bests are sufficiently different from each other, right? There's a diverse hypothesis. So anytime there's a user in the loop, you can present those solutions, and the user can just pick one. So you minimize interaction time. The other thing you can do is you can re-rank those solutions. You can produce some diverse hypothesis and run some expensive post-processing step that ranks these. This is the current state-of-art segmentation algorithm that we have on Pascal segmentation challenge. What it does is it takes an image, it produces close to 10,000 segmentation hypotheses. And these are highly correlated, they're highly redundant, but there are many segmentation hypotheses. Then it uses an external segment ranking mechanism to re-rank these segmentation hypotheses. Now you might ask, if I have access to a ranker, why don't I just optimize the ranker? Why don't I search for the thing that would be the best ranking thing? Ranking can be expensive. You want to evaluate this expensive thing only on a small number of things. Okay? Okay, so if we now are convinced that this is an interesting problem, let me show you how to do this. I'm going to present you the formulation of the problem. So I'm going to be working with an overcomplete representation. I said that each pixel had a variable that could take a label, some discrete set of labels. Instead of representing it as a single variable, I will represent this as a Boolean vector of length k. So there's a vector of length as many number of classes that this node is supposed to label, and an entry 1 in one of the position means that that's the class that this variable takes. So if the entry is in the first place, if the 1 is in the first entry, then xi is set to 1. If it's in the second place, then xi is set to 2. Right? And we disallow configurations where there are more than one ones in the vector or 0 ones in the vector. Right? And you can do the same thing for an edge of variables. Now the vector just becomes much longer. It becomes k square. So you're now encoding all k square pairs of labels that these two variables can take. So if you have 1 in the first place, that means xi is set to 1 and xj is set to 1. If you have 1 in the second place, it means xi is set to 2, xj is still set to 1, and all quadratic of these. Right? And notice that these are not independent decisions. Right? The decisions that you take in edge has to agree with the decision that you take at a node. This encoding is saying that xi is set to 2, and this encoding is saying xi is set to 1. That's not allowed. Right? Why did we do this? Why did we blow up our set of variables? The reason why we did this is now that energy function or this cost function that I showed you, I can write it down as a dot product. I pull out the cost of each label, multiply that with this Boolean vector. It exactly picks out the cost of this labeling, and the same thing at the edges. So it's a nice dot product. Right? And here's the integer program that you were trying to solve. That energy minimization is just minimizing this sum of dot products at nodes and edges subject to mu I and those Boolean vectors being Boolean. Right? That's the integer programming problem. Right? This will find you the best segmentation. And in order to find the second best segmentation, here's the simple modification that I'm doing. All the variables stay the same. Mu1 is your map, so that's the best segmentation that you found. And I have introduced a new inequality that says delta is some diversity function that measures distance between two labelings or two configurations. And I force that that distance must be greater than k. K is a parameter to the problem. Delta is something that you choose. I will talk about both of those in a second. But it's just something that forces you to be different. Visually, what does that look like? Here's what it looks like. This is the space of all exponential segmentations. You were searching over that space. You minimized over a convex hull of this space. So this is the best segmentation that your model thinks that's the map. You disallowed some other segmentations that lied less than k distance away from it. And now when you still minimize over the remaining configuration, you find the second best solution. Right? That's what that visually looks like. So now this is the problem that we're interested in solving. This is the mbest mode problem. For this part of the talk, I'm going to assume that somehow there is a black box that solves the map inference problem. In the second part, I'll go into how we solve that. But given a model, there is some algorithm that solves the map inference problem, right? But this is almost like the map inference problem, but there's an extra constraint. Right? So you can't exactly plug your existing algorithms. What you can do is you can dualize this constraint, which means that instead of handling it in the primal form, in a constraint form, you add it to the objective with a Lagrangian multiplier, which means that instead of forcing a hard constraint, now you pay a penalty of lambda every time you produce a solution that is not k distance away. Right? Every time you produce a solution that's less than k distance away, you pay a penalty of lambda. So this is the dual problem. The reason why we do this is because this is now looking like something we know how to handle.
The previous thing. Okay, so you're actually the further away you are from k, the more you like the solution, right? So
yes.
It's not just an inequality constraint.
Yes, yes. Okay. So if you search over the best lambda, you will converge to the things that, if there is something that's yeah, I'll get to that in a second. But yeah, the reason why we do this is because this objective function now starts to look like things we know how to handle, right? This is an additional term that we knew how to handle. And this, in the literature, if you've seen, this is the loss augmented energy minimization problem. We handle this every time we have to train SVMs or train structural SVMs, right? You add a loss and you minimize your original energy. So this is the problem that I'm calling the M modes. There are still two things I haven't told you about. Delta, so I've traded the primal variable. Now there's a new dual variable as well. And delta, the diversity function that I didn't tell you, right? And you can think about, for each setting of lambda, which is a dual variable, this relaxation provides you a lower bound to the original problem that you were solving. And to get to Rick's question, you can try and maximize this lower bound. What does this function, so I tell you a lambda, you minimize this. What does this function look like as a function of lambda? You can easily show that it's a piecewise linear concave function. So you can maximize over the space of lambda. All right. So let's see. What's the delta? Let's nail that down. What's the diversity function? There are some nice special cases. There are a number of special cases. If your diversity function was a 0-1 function, if you exactly are mapped, then you're distance 0. If you're anything else, even one pixel that you label different, you're some different configuration, right? If you work with that, then this is the mbest map problem. Right? So we generalize that. There are some other generalizations that I won't talk about. We allow a large class of delta functions, and I'll talk about one of them specifically today, which will correspond to Hamming distance. Right? Here's a delta function that I'm going to be working with. It says you sum over each node in your graphical model, each node in your graph, and you take the dot product of the mu I with the mu I of the map. What does this mean? Mu I, remember, is a Boolean vector. That encodes what label you took at mu I. Mu is your new variable. This is just counting how many pixels took the same label as last time. Right? If you take a dot product with a Boolean vector, only when they agree do you get a 1. Otherwise, you get a 0. Right? So this is exactly Hamming distance. Why is this interesting? Well, it's interesting because if I now look at that problem that I was trying to solve, my original energy function minus this Lagrangian times the loss, this loss is now linear in mu. It's a linear function of the variable that I'm minimizing, and it nicely decomposes across nodes, right? So all that happens is that now I have my original node potentials plus lambda times some other constant, right? Mu I is a Boolean vector of length k. Only one of the entries is set to 1, which is the map entry. The cost for the map label just went up by lambda, right?
So just going back to your original formulation, the mu ij's are independent of your mu I. They're additional extra variables?
Yes, so there are some constraints that I've hidden away. Mu ij's are not actually independent. There are constraints that tie mu ij's to mu I,
okay.
yeah.
You have those constraints.
Yeah,
okay.
yeah, those constraints exist. I've sort of just hidden them away because they weren't relevant for now.
So mu1 is always an integer?
In the integer programming formulation, it will always be an integer.
But you're relaxing, right?
In order to solve it, so that's the black box that I hid away. In order to solve it, you will relax it to an LP relaxation. Yeah.
And the constraint that forces only one bit to be 1 is also a constraint in that family of constraints.
A constraint that forces only one bit to be
turned.
Yes, that's also a constraint that's hidden away in this mu. So there are constraints, so that forcing one bit to be 1 is sort of a normalization constraint. If you think of it, only one of the bits can be 1. Once after you relax it, it will become a normalization constraint. And the constraints that they agree with each other will become marginalization constraints. But yeah, they both exist in mu.
One last bit. So you just talked about second best mode.
Yes.
For the third and the fourth,
Yes.
you have different lambdas for different ones, or
Yeah.
a single lambda?
So in the primal case, what you'll have to do is you can add different inequalities that find me at the next best, which is k away from the first, the second, and the third. So you can either have different k's, or you can have some standard setting of k's. So that would say that I just plop down this Hamming hypercube that disallows some solutions. In practice, this is going to be a question of how do I set k, right? And I'll get to that question in practice.
But the lambda is single across. The Lagrangians, right?
So the Lagrangians, yeah, so there's a different Lagrangian for each inequality.
You'll have to optimize over those.
Yeah, you'll have to optimize over those, yeah. Right. All right, so this is nice, that all I have to do now is to modify some potentials. The cost of, so if node I was set to label 1, then the cost of node I taking label 1 just went up by lambda. Right? And I just rerun the same mechanism that you have for map. So if you had a black box, that black box still runs. I just have to perturb the potentials a little bit. Even better is, since I did not modify this edge potential, theta ij, if there was some structure in your original edge potentials, I preserve that structure. So if your original problem was pairwise binary submodular minimization problem, for which you have exact inference algorithms, this new modified problem is still pairwise binary submodular, right? So if there was some exact algorithm for the first case, there's still an exact algorithm for the second case, right? And I think that's the most interesting part. If you have invested some work to extract one solution out of your model, this can extract multiple solutions out of your model. So what does this look like in practice? So here's an image, and somebody scribbled on it. So one color of the scribble indicates this is the foreground, the other color indicates this is background. Here's the ground truth on these images. So this is what presumably you'd like to extract, right? We encoded this with a pairwise binary submodular Potts model with some color potentials. So you look at the color of the foreground, color of the background, set up node potentials, and Potts model. And this is the map that you extract from these scribbles on these images, right? This is the best segmentation. This is the exact second best map. So this is literal definition of second best map, right? Does anyone even see the difference between the first and the second best?
Only in the top row.
Only, yeah, because there's these spurious pixels here that get turned on. The others are different as well. Maybe there's one pixel here that turns on. But so I wasn't making those figures up. This really happens in practice, that you run your entire algorithm again and the second best solution is essentially useless. This is the second best mode that we can extract. So in the first case, we're able to extract the other instance of that object, right? This entire thing was absent in the first and the second. In this one, we're able to fill out the arm of the person that was cut out, right? All by forcing Hamming dissimilarity, right?
The third row, there's not difference.
Yeah, the third row, there's not much difference.
But there must be at least k pixels that are different.
Sorry. Yeah, so the way we're solving this is instead of setting k, we're setting a fixed lambda, which means that you don't actually enforce diversity, you trade off diversity with the original energy with some fixed weighting term, which means that if your original model strongly believes in the original model, you will still return the first solution back. Right. So here's the second experiment that we did. Sorry. Here's the second experiment that we did. This is Pascal's segmentation challenge. For those unfamiliar with this is a large international challenge that's been running for a few years now. The organization that's running this challenge releases the images, but not test set annotations. There's 20 categories on this data set and a background. For each image, what you're expected to produce is this. This is the ground truth. You're expected to produce a labeling of one of these categories for all of the pixels or background, which is shown in black here, right? And what we did was we took an existing model on this problem, which is the ALE model by Vladimir Kolmogorov and Tor. They developed this over a sequence of papers. If you haven't seen this model before, this is just a hierarchical CRF. There are some potentials on pixels. There's some neighboring pixels are joined with some POTS models. Then there's some superpixels and some scene level things. So it's a hierarchical CRF. It took them a couple of papers to develop a good inference algorithm for this model. And all we had to do was modify some terms and run their same algorithm again, right? So here's what I'm showing, an input image. Here's the ground truth. So blue here is I think boat. This is sheep. This is the ground truth. This is the best. This is the map under their model. So in the first case, there's this large region that's labeled as boat. So the segmentation is wrong. In there, the support is wrong. In there, they have labeled it as boat, but the support is wrong. This is actually one of the mistakes that the model does tend to make. Whenever it finds evidence for an object, it tends to smear it across the image. Right? So it labeled everything as sheep. And in this case, it only found one of the instances of sheep. What we did was we extracted 5 additional solutions in addition to the map, right? And I'm showing you the best of those and the worst of those. Best and worst according to ground truth, right? So we are checking ground truth to see which one's best and which one's worst. And in this case, what happens is that you're accurately able to crop out that segmentation. Anytime you change segmentation, this is hamming, so you get rewarded for being different from that. In this case, you're actually able to get out that original support of that object, get an actual segmentation. And then in this case, you're able to get the other instance of the object. So not just one sheep was present, but a second one was also present, right? So these are examples where we find large improvements in the additional solutions that we extract. These are examples of medium improvement, where again, this is the ground truth. This is what the map says. In this case, there's a horse and the rider. They're both labeled as the horse in the map. What we did was extracted the horse out, the rider out, lost some part of the horse, right? In this case, everything was labeled sofa. We were able to extract a person out, lost some bit of the sofa here, right? And in this case, we were able to extract an object out here from the map, right? These are examples of cases where it doesn't make a big difference of running these additional solutions.
Sense for at the beginning of the talk, you mentioned approaches where they just try, unsupervised segmentation approaches, and like say you get 10,000 possible ones. You could do the same thing here, where it's the best.
Yes.
Relative to ground truth. Did you do that?
Yes.
Does that do better, or do you still even with 10,000 random examples, essentially random segmentations, does it still not do as good as your approach when it's?
Yeah. So you're asking whether we did a re-ranking on these?
Yeah.
Yes, we did. So what I'm showing here are comparison are empirical results. So this is intersection over union criteria. So you produce a mask. There's a ground truth mask. You measure intersection over union. That's how accurate this mask is. This is the average over all categories. Here's how well just the map under this model performs. So it's about just under 25. MBEST map in this case is a non-starter. This algorithm is actually more difficult to implement in the MBEST mode because it's not just one map computation again, it's order n, where n is the number of pixels, that many computations again. So in this case, we did back of an envelope calculations, it would take us 10 years without parallelization to get each additional solution. So we just don't have that. And in practice, it doesn't seem to make any difference anyway. We did implement a baseline which would look at confused pixels and flip them to the next best thing. Here's the oracle numbers for mbest mode. So if you extract 5 additional solutions in addition to the map and took the best looking at ground truth, so that's cheating. Right? This number is not a valid entry to Pascal because you can't look at the ground truth. Right? So this goes from about 24, but this tells you how much signal there is in those additional 5 solutions. Right? You go from about 25 or so to over 36. And to tell you the scale of these numbers, the state of art on this data set is just about 36. Right? So you took a model that was nowhere close to state of the art and is now beating state of the art. Well, beating in the sense there is a solution in these 5-ish. So the goal here is now, can we re-rank these solutions, right? Can we take these 6 and run that re-ranker? We have an initial experiment on that already. We've taken the ranker from that work, applied it to these 6. It already improves on the map, so we're able to do better than the map, but we haven't yet realized this potential. So we're still tweaking that re-ranker to see if we can do better. Intuitively, it feels like it should be an easier problem than re-ranking 10,000 segmentations, because now it's just 6, right? 1 out of 6 re-ranking is much easier. And we hope this number to...
You don't have the 10,000. It'd be great to see the graph of the, if you have 100 random, 1,000 random, 10,000, see how many random, how many random segmentation, how many you need to get up to 35%.
Yeah, so I don't know. So this line is them re-ranking 10,000, right? So this is them. The state of the art is them, but them re-ranking 10,000. I don't know if there's a curve on ranking as you go fewer and fewer.
Were you using their ranker or you came up with your own?
No, right now we're just using their ranker. We're adding some new features, retraining it on our own. So this is not the latest that we've been able to achieve, but just off the shelf, if we take their ranker and run it on ours, this is what that does.
Okay, but there's some number between their 10,000 and your 5, right?
Yes.
Whether it's forcing them to generate fewer or forcing your algorithm to generate more.
Yes.
You have 2 curves, right? Which is your best K and their
best
K or whatever they're doing, right?
Yeah.
Helps them converge.
I don't have access to... I can't really generate, so I'll have to check their paper to see if that curve is available. I would expect that their curve, that they really need many segmentations, because if you do a coarse job, because all they do is they run ST min cuts at where S and T, they say this pixel, I assume this pixel is foreground, I assume this other pixel is background, and I run a segmentation on this, and I just do this for many locations of source and sink. Right, so it's just completely dumb procedure, and I'm fairly certain that you need a lot of locations of S&T to do this.
It's a different MRF than AL, right?
Yes. Yeah. All right. So the thing that I'm interested in and that we have been doing with this is, we've also taken pose estimation problems where the goal is not just segmentation. The goal is not segmentation, but the goal is where is the arm of this person, where is the head of this person, where's the leg. So this is a different MRF. It's actually a tree graph, but your labels are locations. Where are these people? And there has been some preliminary work on trying to find multiple hypotheses. We have the implementation of Deva for the best case, and we're modifying his code, and we're finding improvements on that as well. But there are a lot of other applications that I think that can benefit from this. I think this can really improve parameter learning as well. The way we train our models right now is we run a for loop. You use your current setting of parameters to ask it what's the best segmentation it believes in. If it's not the ground truth, you modify it a little till the ground truth is what wins, right? And if you had access to not just the map, but also some other modes that it believes in, you can converge much sooner, right? Because you're extracting other things that this model believes. And there are connections to rejection sampling in this. But just to summarize this part of the talk, I think here's what I'd like you to take home from this, right? You're working on some problem, right? So think about the problem that you're interested in, whether it's ranking documents with some retrieval setting, or whether it's structure for motion. There is some discrete aspect to it, right? And the key thing is, are you happy with the first best solutions that you have? If you don't have the perfect models, then you're not happy with that. And if you're not happy, then you should look at extracting multiple solutions out of your model. And we're hoping that this can help additional applications as well. Right. Are there any questions about this part before I move on? All right. Okay, so the next few things will go much quicker because I'll go into fewer details. But here's the second part of this talk. I want to introduce a notion. I'll give a high-level picture. I won't go into all three of the things. I'll just give a high-level idea, and I'll go through it. We came up with this idea of focused inference, and we applied it to a few different applications. So I want to just tell you what focused inference is. So I told you there's this integer program that we're solving. In the first part of the talk, I assumed that there's a black box that can solve it. Typically, these things are solved with, for example, linear programming relaxations. So you were going to solve this linear function with some discrete variables, right? That was a linear function, right? So I can take all your parameters, make a really long vector. I can take all your variables, make a really long vector, and that's just a dot product. And now the constraints that I had hidden away, that I didn't talk about before, they're also linear constraints. So this is the exact form of the optimization problem that we're studying. It's a linear objective function, linear constraints, Boolean variables, right? And what you study is an LP relaxation of this problem, that you replace the Boolean constraints by 0 to 1 constraints, right? This is a continuous relaxation. And what that essentially involves is replacing the convex hull of the solutions by an outer bound, right? This outer bound looks like a more complicated structure in 2D, but it's actually a simpler structure to optimize over because this is a very high dimensional space. In 2D, it looks more complicated, but it's actually much simpler. And the way we solve these linear programs is by message passing algorithms. I won't give you all the details, but essentially what this involves is you localize each part of the graph, solve a problem on that part of the graph exactly, and then you pass messages. Here's what I think my neighbor should be. And that takes you to the linear programming solutions. You can interpret these messages as dual ascent algorithms, right? But in a sense, this is a highly inefficient procedure. What we wanted to do, this is what is done right now, and what we wanted to do was improve this procedure because our observation was that data does not look like this. We don't have complexity at all scales, at all nodes, at all relative locations, right? Our data really looks like this. There are regions of complexity, but there are large regions which are essentially simple. I can look at the local potentials and I know what it's going to be, right? And if I had to give you an analogy, I would say that the first approach of passing messages everywhere is sort of like a carpet bombing approach to inference. Indiscriminate deployment of computation, right, everywhere. And what we'd like to see is a more focused deployment of computation, where you find the important parts of the problem and you only focus your computation there. Right? So here's the key hammer that I'll explain really simply. We were going to solve a linear program. Corresponding to the primal linear program, there's a dual one. This is LP duality theory tells you that there's a dual linear program in terms of the Lagrangian multipliers of your problem. We know from duality theory that the primal decreases. Each setting of the dual gives you a lower bound. So the dual increases as you spend more computation. If the two meet at any point of time, you know you've converged, you've solved the problem exactly. Moreover, because these are linear programs, you know that complementary slackness conditions are exactly conditions that you can check for convergence. When these conditions are satisfied, you know that you have solved your original problem, right? In our work, what we essentially did was instead of using them to check for convergence, we used them to guide where messages should be passed. We distribute them at various locations in the graph and tell you which are the important regions in the graph, right? These conditions distribute nicely over the entire graph. And that's the most important concept here. That's the key hammer, right? And we were, in a couple of papers, what we were able to show was that we can say some precise theoretical things about it. We can say that this is a generalization of complementary slackness conditions. We can say that it's exactly a notion of distributed primal dual gap. At any point of time, you have a primal dual gap, you have a best primal, you have a best dual, and the sum of these scores sum to that primal dual gap. And these are really cheap to compute. Constant time for each edge, you can compute this score. So it's not like you have to spend computation to compute this score to help computation, right? It's really cheap to compute. So we applied this idea to a few different things. One was distributed message passing. How do we speed it up? So in this case, here's an image, here's a current segmentation. You update this segmentation somehow. So in this case, let's say a user says, all the white pixels here are where your model has been updated. So a user says, I think this is background, or you might have data coming in streaming for the next frame, so the model has changed everywhere. and you get the next segmentation. But this is the key result here. This is what would happen, the dual and the primal, if you were to pass messages everywhere, to go from here to here. And this is what happens when you use our method to find the important parts of the region and only pass messages there. You essentially converge much sooner, and the x-axis, notice, is in log scale. Here we're converging 350 times soon. What is this baseline that I'm talking about? That's the TRWS implementation of Vladimir Kolmogorov. And so if you've played around with that implementation, it's an extremely efficient implementation and not an easy one to beat. In this case, we're able to beat it by this big margin, and in the other case, we're also able to beat it by a big margin. The reason why we're able to beat it is precisely this figure right here. It's showing you where we passed messages. So the white pixels are where potentials were updated. Small number of updates, large number of updates. But it only passes messages where things really matter, where segmentations are changing between the two frames. Right? And that's exactly why you converge so much sooner.
So why does your purple graph start off higher than the red graph?
I think what's happening is that this is log scale, and I'm zooming into the region that's closer to convergence. So it might be worse off initially, and then it's beating to convergence. You can alternate between the two. You can start off here and then at some point of time switch to the other algorithm. This algorithm, the baseline, what it's doing is it's passing messages horizontally and then vertically. So initially it makes big improvements, but later it gets stuck in this process where it has to pass lots of messages. Our stuff is finding edges where messages need to pass and only passing there. So initially it doesn't make a lot of improvement, right? Because it keeps passing messages locally. So there's some things, segmentations have to change. So somehow this node has changed, it needs to let its neighbor know, its neighbor know. So it takes a lot of time initially, but it converges much sooner because you're only focusing on those.
So, the classic, at least that style of process, the TRW has a horizontal and a vertical sweep.
Mm-hmm.
Have people looked at hierarchical pyramid or whatever you want to call it, based techniques where the propagation looks more like it's happening, on
at multiple scales?
Yeah.
Not that I've seen. I mean, so scheduling, which is what I'm presenting, isn't certainly new. I mean, people have looked at scheduling before.
Right.
And some things that people have looked at is, let's see where the messages are changing more. Right, so if the last time you sent this message, this time it's essentially the same, then maybe you shouldn't send this message. Maybe somebody else should send this message. I have not yet seen hierarchical. So I know Pedro looked at this a little bit, but that's essentially constructing a hierarchical graph. Like you have to construct a different graph.
You have to, if you're going to exploit hierarchy, you have to construct a different graph because there are no connections that let you jump.
Yep.
It's not clear you want to introduce those. But if
Yep.
you have sort of an auxiliary graph that is supposed to mimic a lower resolution version of
Yeah.
this, in whatever that means, right? It could be used as a hint graph, right? It
Right.
could sort of, you could propagate stuff up
And then
coarser level and then propagate
that
it
propagates
down.
down, yeah.
And then you kind of say, well, did my LP at the fine level kind of move forward faster because the information got over faster,
Yeah.
right? So, this raster order propagation is extremely efficient if you really have a tree, right? It's
Yes,
optimal.
that's optimal.
But in general, it's not a bad heuristic. It's, in the linear system solving literature, there's stuff called alternating direction implicit, which is, decades old, but was proven to not work nearly as well as multigrid, right?
Mm-hmm.
And now the algebraic multigrid. The idea of creating coarser spaces that adapt to the actual intrinsic connectivity of the underlying thing. I mean, it's something I'm very interested in. I've only worked on the linear, which would, be equivalent to the quadratic energies or the Gaussian MRF version.
Right.
That's all I've worked on, but I've been
Right.
dying to start working on the hierarchical for general inference problems.
Yeah. I think that would make a lot of sense because that way you can, that way you can make large regions flip their labels
Right.
by just going one layer up.
Yeah. I'd be worried about this method when you have a large region is that it wouldn't choose that region to actually update the messages because they all have a little bit It's a little bit of change.
Yeah.
Is that a problem?
So one thing that I showed was that the scoring function, the way I wrote down the LP and I said, look, I can score every edge. Our formulation extends to scores over regions. So you can compute scores over large regions as well. So even if every edge has a little bit of score, the sum might still be the most important part. And so you might decide to go up if you had written a hierarchical
If you have a hierarchy.
Yeah. But if you haven't written a hierarchical, then you're kind of stuck. Then
I can see like the energy, it's always just be kind of below that threshold and never.
So in order for them to be below a threshold, there has to be something else that's always winning, right? There's this big edge that thinks here's where the most problem. All right. So these things really help. You can make things really faster. In fact, we applied the same idea to another direction. We said, I said that, look, you can compute scores on these edges, and I can tell you which ones are important edges. But that was all assuming that your original LP was a good LP to begin with. That it's a good relaxation. This is an NP-hard problem, so a lot of cases are going to look like this. The best lower bound you can extract is nowhere near the best primal that you can extract. And so our formulation, there's not a single LP. There's tighter and tighter LPs because you can add more constraints to your original linear program. And our formulation, the first LP was saying that that edges are consistent with nodes. That the labeling that you give at edges is consistent with the labeling that you give at nodes. You can write down tighter LPs by saying that triplets are consistent with edges. That the labeling that you give at 3 nodes are consistent with the labelings that you give at edges.
Sorry, the original pair to nodes is that question of mu ij
Yes.
at the right marginals?
Yes.
And what's the triplet version?
For the triplet one, you would introduce a new variable, mu ijk. So it would be a k cube long Boolean vector, and you would force it to be consistent with something else. Your original energy is still pairwise, so you don't care about optimizing over mu ijks. Its objective function would still be 0, but it plays a role in the constraints. And that tightens the LP because now it has more constraints in the LP. Right? But the question here is, while we could reasonably think about adding all edges to the original LP, we can't think about adding all triplets. I mean, n nodes, lots of triplets. You can think about tighter relaxations on 4 nodes. How many of these things are we going to add? And so if there was a way to score...
So why can't you add all triplets? If it's originally a mesh graph,
Right.
there's still order n squared triangles, right?
So if you restrict yourself to only the original triplets that are present in the original graph, then perhaps you can think of adding them. But long-range triplets can also tighten your LP, which might also be interesting to add. So you can include edges that don't exist in your graph, but that can still help tighten the LP. So then you really have to consider all n cube or n choose 3.
So philosophically here, you're making a big jump because the original thing was you encode the problem as a continuous optimization or an integer program, right?
Right.
Where it's assuming the constraints are met, right? It's exact, right?
Yeah.
Now you're saying let's just throw in lots of extra constraints so that the solution can proceed faster, right?
No, but even with these constraints, it is still the original problem because think about what was happening. If I think about it this way, what is the worst I can do? That I introduce a variable that depends on all pixels, and so instead of being k square or k cube, it is k to the n, right? What are the constraints I can add to this? That it sums to 1 over all possible labelings, that you choose only one labeling, and that each of these labelings is consistent with the sub-labelings that you have, right? That type of constraint would still be a valid constraint to your LP, right? In fact, if you threw that in for all the cliques in your tree decomposition, so if you wrote down a junction tree of this graph, and if you wrote down as many constraints as the tree width of that graph, then your LP is guaranteed to be tight, and we can show that you just need to add as many constraints as the tree width, and then your LP will be tight in the worst case. So we're essentially moving towards that by adding more and more constraints. And the thing to think about is we can't add all triplets or all 4 things or all 4 pairs. And so if we could somehow score these things, that would be helpful. Right? Which ones should we add into the relaxation? Can you know a priori? So when you add a constraint, it will help, obviously, because it will tighten the LP. But can you, before adding it in, know how much it is going to help, or have an estimate of how much it will?
When you say you can't add all of them, right? If the triangle consists of 2 real edges from the original thing, right, plus the extra edge, there's only constant, if you start with a regular planar grid, there's only a constant number of such triangles, right?
Right.
And why would you want to sort of take 3 nodes that are all over the map and make up a hypothetical triangle over those 3, right? So in other words, it's just using locality almost as good as using something based on local gaps, right?
Right. So you can think about, you can enumerate. What you're saying is it's really easy to enumerate over all the local triangles. Yes, you can do that. What about when you go much higher, 4, 5, 6? Then that space is becoming much larger, and even enumerating over that space becomes complicated. And what I'm trying to say here is there a way to construct these cliques where I can sort of localize that this is where my primal dual gap is coming from? Can I directly construct such a higher order clique and say, so all the edges in this neighborhood have little bit score. Can I just add this entire region as a clique into my relaxation? And that's what we looked at here. And that's what essentially what we did for this problem. There was an original image. We had access to a blurry, noisy version of this image. This is we set up an MRF problem for denoising and deconvolution. This is the best primal that we could extract out of the pairwise linear program. So what I was showing before, and this is the best primal I can extract from the triplet LP. If I add triplets into this, it becomes tight. This is the actual integer map. So that's fine that we can extract this from this. Here's the objective function, not the objective function, the primal dual gap decreasing as a function of time as I'm adding more and more constraints. So if you add constraints randomly, so if you randomly throw in triplets, not random triplets, but if you enumerate over them and randomly throw one in, then here's how primal dual gap is decreasing because your relaxation is getting tighter. And here's if you choose using R score. So it's converging to 0 much sooner. You're on some levels, you're essentially 3 times faster. At the end, this guy is converged, this guy is not even close to convergence. Right? That's the idea.
And what's the intuition when you watch it select triplets? What is it typically selecting?
Typically, it's selecting things at the boundaries. So it's selecting things at object boundaries. So like here, it might select some triplets here. So in a sense, it is using locality of the problem, but still it's getting a one step above edges.
Right. So it's locality based on the actual
graph.
Smoothness of the graph inherent in the blurry image, right? Or in the solution, which is it looking at? Does it tend to sort of look at the current solution and that's what drives it, or is it more look at the original input?
No, I think it's looking at the best solution that it can extract and the best dual value it can extract, which is a function of this. So it's looking at both. What is the best primal and the best dual? Okay. All right.
You're reasoning about only on triplets, but not on all sets of multiple sets.
Yeah, in this case, I was reasoning only on triplets, but the formulation extends to arbitrary size subsets.
But can you do them all together, like 3s and 4s? And then
yeah, so you can construct them from their subsets. So you can score. So at any point of time, you can only score the things that exist in the relaxation. So if only edges exist in the relaxation, I can compute scores on edges. And summing up the scores of edges in a triplet, I can compute scores of edges. So I can't give you. So yeah. So if I had to compute a score for a set of 5, then I would have to look at all 5 choose 2 of those edges that exist now, and I would have to sum their scores up. Does that make sense? All right. So let me try to finish up quickly. I won't go into the last part, but we also took an algorithm, alpha expansion, which at the surface of it looks nothing like an LP relaxation. It looks like a greedy algorithm, but people have interpreted it as solving that same LP. And we were able to use this idea to also speed up standard alpha expansion by factors of 2 to 3. And that's what I'll say about that. So, in general, I'm interested in extending this to QP relaxations. I talked only about linear programming relaxations. I'm interested in, a lot of the methods I said are natively parallelizable. So one of the things that I want to do is have parallelized implementations. There's this really nice work coming out of CMU, which is GraphLab, which lets you work at a really high level. You specify your algorithm. It does all the low-level parallelization, and it's for multi-core and for distributed settings. And there's a chance that there's a good chance I'll be working with Carlos Questin's group at CMU and taking some of my algorithms to GraphLab. And I want to also look at focused learning, so trying to do this scheduling for learning problems, and I think there's some interesting scope there. Okay, let me show some teasers, and I think we should be done in like a minute or so. In my PhD thesis, I think a lot of people here have seen this before, but we worked on this problem of interactive co-segmentation, where you have a large collection of images, and somebody with the same object appearing in these images, and you can build this system. We built the system where someone can just scribble on a single image or a few images, say that this is foreground, this is the object I'm interested in, and our system would go ahead and segment that object not just in that image, we'll see that, but in the entire collection of images. And this, in this case, you have to look at all the images, and so we also looked at active learning formulations, where the system would tell you where to go next, where should I need to see scribbles next. This was mostly for building an automatic collage, so you scribble once and you build a collage. But what we were able to do was also extend this with Adarsh Kaudle, who was an intern here that people here are familiar with. We were able to extend this to volumetric reconstruction by using a shape from silhouette algorithm. So you use a standard structure from motion pipeline to find camera settings, project the silhouettes back into the 3D to carve out a volumetric reconstruction. And this is the cutest part. I'll skip this video. This is the cutest part. Others just got hold of himself with a 3D printer, so he was able to actually produce these little tiny structures from this. These were printed using a 3D printer using our algorithm. So just a couple of images, you scribble. It was able to extract. It was able to produce the 3D model and print it on a 3D printer as well. In general, I've worked on some other problems like single image depth estimation. Maybe we can talk about that if we end up talking about this. We have a really nice algorithm coming that's the first max margin learning algorithm for Laplacian CRFs, which are models that are really effective for this problem but hadn't been looked at before because their algorithms didn't exist.
What is the Laplacian CRF?
So Laplacian CRF is a CRF where the edge potentials have L1 norm terms. When you have L1 norm terms, it's not a log linear model, and so some of the existing algorithms don't work because they make a log linear assumption. And so we came up with the first approximate max margin algorithm for training some of these things. In the past, I've also looked at some retrieval problems where, suppose you have an image and you're trying to find out what is the content in this image. So I give you an image, you give me a textual description. And this was an algorithm that we built that would first segment it, search for images with respect to this segment, and then do some textual analysis on that to answer your query, essentially. All right, there's been some work on similarity learning again. Also, so with that, I'll stop. Here's the co-authors that were involved in some of these things, and that's it. Thanks.
Any additional questions? That's a lot of questions during the talk. So. Great. Thanks.
Thanks.